All right, good afternoon, everyone. I'm Mohammad, and I'm going to here tell you about hierarchical integration of WebAssembly in serverless systems. I'm here on behalf of my student who couldn't get a visa, unfortunately. So hopefully I can answer your questions about details. Serverless computing has gained lots of traction over the past few years. Part of the appeal is that auto-scaling provisioning aspects is fully offloaded to the provider. So it's appealing for customers and developers. Partially also it's appealing because you only pay for what you use. So it's not like a VM that is just sitting there and you have to pay for underutilization. As you have no traffic or low traffic, the scales of your replica goes down, and then when you have traffic again, it goes up. So it's basically appealing in that sense. And as a result, many people end up using it in the cloud. There are some reports, according to Datadog, that half of customers on Amazon use AWS Lambda one way or another. And then AWS Lambda is a function as a service offering. There are different types of serverless, container-based serverless, and different services on different providers. Despite the fact that serverless allows you to not pay for when you're not actually having traffic, it ends up being more expensive per unit resource, per unit time. In fact, last week we had a paper at EuroSys that we carefully analyzed different reasons why serverless can be expensive. But to just give you a sense, it can be up to 2x more expensive compared to VMs, especially if your traffic doesn't have that fluctuation. And as a result, you hear these stories in the news that a big team moved away from serverless and they saved a lot of money. In this specific case, this was the Amazon Prime team that moved from AWS Lambda to EC2 and saved a lot of money. So that's shocking. Now, if you think of one of the reasons why serverless is expensive, there is this interaction between the pricing model that forces the providers to only charge for what they actually people run their applications for. And it means that when there is no traffic, they are the one in charge of scaling things down. So this auto-scaling becomes a burden on the provider. And in case there is any sort of inefficiency there, that is overhead. That basically indirectly reflects itself into cost. They also are in charge of scaling things up or maybe keeping some resources around to prevent cold starts. That's the latency when the traffic comes and there are no resources available to run it. We want to prevent that. What makes the matter worse is the fact that execution times in serverless are really short. So here are distributions of execution times on different platforms, starting with Azure 19, Azure Functions, Azure 2021, Huawei, IBM. These are different platforms measured in different time, but all of them, for those we see that more than half of the applications have an execution time of average less than 1 second. In fact, newer traces, Huawei 24 and IBM, which we released last week at EuroSys, show that more than half of the executions are less than 100 milliseconds. So when your executions are so short, any sort of system overhead can become, a burden, especially because you can't pay, you're not charging customers for that. To make the matters worse, the amount of resources that people ask for these serverless applications are also very tiny. So roughly half of application ask for sub-core amount of requests. So imagine that a function comes, runs for 100 milliseconds, and only asks for 0.1 cores. Right? So everything else, bringing up a container, taking it down, becomes heavy overhead. So is the case for memory configurations. So with all of this context, one question that one might ask is, well, is there a way to amortize the overhead of scaling or the platform overhead overall across different customers? The idea could be if we could group apps together, maybe we can share a certain number of resources and reduce costs associated with keeping containers alive or starting containers. And perhaps even we don't need to start containers all that much. To make the case here, we analyze these traces from Huawei, IBM, and Azure. And we see that, in fact, when we start bundling different applications together, the coefficient of variation of invocation goes down. And this makes perfect sense. This is nothing secret. Because if you have one application, of course, the traffic fluctuates a lot. When you add the second application, chances are that they would cancel out each other. And as you add more and more applications together, the traffic flattens out. And in fact, that's the statistical foundation of how cloud economic model works. Traditionally, we've been doing that with physical hardware and VMs, right? So if you needed some application to run, it doesn't make sense to buy your own physical machine. You go on the cloud. It's cheaper because cloud also serves other people who might have traffic in different times. So the question we are trying to answer is that whether we can do that sort of co-location, but at a higher level of abstraction, not at the VM and physical machine level, but at the level of serverless functions. In order to pursue that question, we have to understand some basics of how different isolation models work. One way to go is to go for very fast processes, or threads for that matter, that are extremely efficient, but not as secure. So if you have a bunch of co-tenants running together, it's not safest to actually run them on different processes, because chances are that they could access each other's data, and that's not great. We could go all the way to running each application inside a full-fledged virtual machine, but unfortunately, that is slow. It takes tens of seconds to bring up, but it's extremely secure. And you can imagine there are different data points in between, lightweight VMs, containers, different technologies. And in particular, our work focuses on using WebAssembly. So for those not familiar, WebAssembly is a near-native binary instruction format originally designed to run code on the client machine. Basically, we want to have compatibility. We bring code on the browser side, and we run it no matter whether it is Intel machine, ARM machine, this OS, that OS. But over the past few years, it has gained attention to run code on the server side. Part of the reason for doing that is that these things are low memory overhead. They are extremely fast to boot up, orders of milliseconds compared to containers that can be tens or hundreds of milliseconds. But during execution, they're a bit slower than native run and running in containers. WebAssembly has gained traction, especially in the context of edge. Companies such as Cloudflare or Fastly offer you, serverless workers or serverless edge workers that run purely in WebAssembly format. So you compile your code into Wasm binaries, and they run it for you. Very effectively, very efficiently. It is very cheap also. However, when it comes to the cloud side, in terms of general purpose serverless, still the community is deciding what's the right way to do so. There are some school of thought that says, okay, maybe we can use Wasm as a runtime, meaning that instead of using containers, as long as I am OCI compatible, OCI is a standard open container initiative, I can just hook it to whatever system that was container-based, and everything would work just fine, which is the case indeed. And the benefit of that approach is that you adhere to standard interfaces, you leverage existing capabilities of the platform. You don't need to redesign everything. But as we show in this paper, that approach is not really efficient in terms of tapping into all the potential of WebAssembly in terms of increasing density. The alternative approach that is pursued mainly in academia is, well, let's go design an entire serverless platform around WebAssembly. And a great example of that is the FASM that opened the door for a lot of researchers. They have shown that if you do so, the density of your application goes up significantly. But the downside of that approach is that you're basically throwing away a full platform just because you want to use WebAssembly. The other downside is that WebAssembly is not rich enough yet to support all different types of applications, and it would be too much to burden developers to go rewrite everything, change everything to just run in WebAssembly. So in our work called Wasabi, we're trying to hit a balance between the two elements of ease of integration and system specialization. So our idea is that what if we can actually increase the density using Wasm, but also we make it really easy to integrate with existing platforms that have been built for years. There are millions of lines of code. We don't want to redesign. And to make the case, I just want to give you a sense of what happens in some of these serverless platforms. This is over time. The x-axis is time. Y-axis is the resources allocated. You can see that there are different applications. Each application can have one or more containers. Depending on when the traffic comes, if a container is around that has capacity and is set to have concurrency greater than 1, that request can go there for that application. If not, if it is the first time we see that, or if there's not enough capacity, we need to start a new container. And you can change this container to any sort of sandbox technology, lightweight VM, doesn't matter. And that would incur a cold start. What we are advocating for is an alternative architecture where you still have containers around, but within those containers that now are larger, you put a lot of WASM modules. And the idea is that depending on your organization's thread model, you may or may not be actually able to co-locate applications from the same organization or subsets of organizations, or maybe if you're really loose on your thread model, you can even co-locate everyone together. Now, the minute you do that, because the interface, the main scaling interface for the platform is containers, you can still support heterogeneity. You can have containers that are just running whatever application that is container-based. These are images that could be already built. They're working just fine. But you can also simultaneously support these sort of new applications that are able to compile to WebAssembly in parallel. So our system, Wasabi, basically has multiple components. The main component is what I just told you. That's the goal of our system. We want to have a hierarchical isolation architecture where the units of scalings are containers. However, inside these larger containers that what we call WASM boxes, we can put lots of WASM modules. However, to make the entire system work very efficiently, we needed to change a bunch of other elements. For instance, we needed to provide resource server auto-scaling, resource server admission control. We do some degree of overcommitment, container right-sizing. We do memory pre-allocation, and we do thread-level cgroup isolation for additional safety within a container. Because this talk has a limited time, I'm not going to go into every single element of this design, but you can imagine that it is involved. Please look at the paper, but I'm going to highlight some of the more important ones now. So one thing we needed to upgrade in our system was that admission control and auto-scaling cannot be concurrency-based anymore. Because as you start packing different applications that have different execution times and different resource consumption together inside these containers, you end up being in scenarios that sometimes with low concurrency, you run out of resources. Sometimes with high concurrency, there's still resources available. So we actually had to look into the degree of resource consumption, both for admission control at the container level and also for auto-scaling of our containers. So that's something that we had to change compared to existing platforms. The other thing that was very interesting to me personally was how WebAssembly is actually slower compared to native code when it comes to memory allocation. And that has to do with memory bounce check that happens. And especially if you go ahead and give people subcore allocation, it can take you a really long time to allocate memory. So the trick that we do here is that we start by having a full core. We quickly pre-allocate some memory. And then we reduce the core size, and then we start running the WebAssembly that has to run. And in doing so, if you do it just right with the right degree of memory pre-allocation, you can hit a balance between giving the performance boost and also not wasting lots of resources. We implemented this idea on top of Knative, which is a production system, open source system used at Google Cloud Run and IBM Code Engine. It's almost 2 million lines of code, and it took us less than 2K source lines of code to add this change. And that's what I mean by imposing no overhead, no serious overhaul to the system. We use WASM-Edge, but you could use different runtimes. We have a cluster of 8 nodes with around 100 cores and 200 gigs of RAM. And we use some subtraces from Azure. Comparing ourselves with Knative, state-of-the-art system, Knative versus WASM-Edge, which is just direct integration of WASM as a runtime, and a spin on top of Kubernetes. Here, you can see over the 2-hour window of our experiment how the resources are allocated in our cluster. We can see 2 observations here. If we use WASM just as the runtime, we see some reduction in our resource allocations, but not that significantly. So here, if you compare Spin or Knative plus WASM-Edge compared to just basic Knative, you see that the resource allocation comes down, but not that much. With Wasabi, we can reduce it almost 10x. So significantly, we can reduce the amount of resource allocation, both for CPU and memory. The other thing is that it seems like grouping different applications on top of same containers has some improvement for resource efficiency that I'm going to show you in a minute. We do so without hurting the service time. Service time is basically the end-to-end latency minus the network round trip time, because that's the time that you spend inside the system. And here you can see the distribution of service time for different requests. Wasabi gives you the best performance, both in terms of average and also in different percentiles compared to these systems. And we found out that the main reason for such gains is actually from the fact that we have fewer scaling events. Because now we use larger containers, we only end up in these 2 hours starting 16 containers for all of this workload, compared to Knative that starts 1,000 times, roughly around 1,000 times. So that's actually where we see most of our gains are coming from, both in terms of eliminating scaling events that can be wasteful in terms of resources, also in terms of making sure that we are not having cold starts, right? Because if your containers are warm, effectively your service time also goes down. So that's where we get both the resource efficiency gains and also the service time gains. This is another experiment that shows that, well, if we don't have the co-location effect, if I just run the single application in my cluster with the highest rate possible, I only get around 20% density gains from Wasabi compared to Wasm-based within Knative. And that tells me that a lot of our gains is coming from co-location. So please refer to our paper for more experiments. But to conclude, we are proposing a hierarchical isolation mechanism for WebAssembly in the context of serverless. This requires really a small amount of code change. And of course, you need to do lots of optimizations to get it to work. This has been adopted, components of it inside production at Huawei's Cloud Edge Serverless. If your team wants to deploy it in production, come talk to me. We'd be happy to help you. And I would be happy to take any questions.